Okay, so good afternoon, morning, well, whatever you are, greetings. My name is Bianca Marques, and this work is about data acquisition for modeling the convective drying of Yacón slices. This work was developed between Université de São Paulo in Brazil and AgroParisTech in France. And if you've never heard of Yacón, don't worry, that's normal. It's not that popular yet. So Yacón is a plant originary from the Andean region, namely Peru. The edible part are the roots. They're normally consumed fresh. There are other options, like you can cook them, you can make chips, you can dry them and grind them and make flour. But the important part is that they are sweet, and when fresh, they are crisp. And they feel more or less like a pear. And although they are sweet, they are very poor in simple carbohydrates like sucrose and fructose and glucose. Instead, most of their dry weight is made up of inulin and fructooligosaccharides. These are also carbohydrates, but the human body does not have the enzymes to digest them. So they go through the gastrointestinal tract intact. They are even recommended for diabetics for this reason. And they have this property that when they go intact, they feed some good bacteria in your colon, like lactobacillus, bifidobacteria. This is good for your health overall. So, well, it's tasty, it's good for your health, everything's fine, but they have a very high water content, about 90% of the fresh weight, and also a very high water activity. And this leads to a very short shelf life, about a week, up to 10 days, and then they spoil. So the simplest solution for that is you dry them. To dry them, you must cut them. But these roots are very rich in phenol oxidase, which darkens them. It's an enzyme. You cut them, they go dark, very fast, like minutes. So to avoid this, to make a product that looks good, appetizing to the consumer, normally the roots are blanched. This process happens with either hot vapor, water vapor, or a chemical like an acid or a sulfate. When you blanch, when you dry the Yacón roots, we cannot guarantee that these compounds of interest, the fructooligosaccharides, the inulin, they are intact. They could be bleached, they could be hydrolyzed. So our main goal with this work is to accumulate data to understand very well the drying process of Yacón roots. So with this data, we can make this process the best possible to preserve these compounds of interest, to have the best possible final product. How do you do that? So this presentation is all about the experimental work. We had to acquire all the data we needed to simulate it later, to understand it as best as possible. So in this experimental part, we have tried to see what's the best drying condition and how does my material work in terms of soluble solids, of sorption isotherms, of kinetics, all this. So we will feed this data to a simulation, and in the end, we will see if that process actually protects these interesting compounds. We began our work naturally by Yacón. These roots were locally sourced from a farm in Brazil. They came in boxes of about 17 kilos, and there were all sizes and shapes. Some were injured, we had to discard them. So we have packed them and put them in a fridge until use. We use them, drying them in this oven that we have in our laboratory. And this oven is made up of three parts. The oven module, we call it chamber also, the control module, and a microscope upon the chamber. So this oven module is made up of a shell made of steel, and we have 4 trays. Each tray is placed upon a scale, and these scales send data to the control module. Above this chamber, this metal shell, there's a quartz window that is transparent, and upon this we can put a stereo microscope that is specially calibrated to measure with this image that it acquires the radius of the sample. And in control module, it sends the air to the drying chamber and is also capable of recording this weight, this airspeed, humidity, temperature over time, or in real time. So for those drying experiments, we have selected these roots with enough size. Then we have cut them with a round cutter and uniformized the height also. We have blanched the samples in citric acid, and we have placed the samples upon one of those trays of the drying oven. And we have dried them in 4 conditions: 50 degrees Celsius for 20 and 30% relative humidity, 60 degrees Celsius for 20 and 30 also, for a minimum of 5.5 hours. And other characterizations we made were we measured the soluble solids content for fresh roots. We took 4 roots, and in each root we measured in 1 point. No, in 4 points. And we also measured the real and apparent volume. These tests were made with roots in different stages of drying. We took some samples, we put them to dry, and we took them out at different times, 1 hour, 2 hours, 3 hours. Then we had these measurements done. And finally, we have acquired vapor sorption isotherms in either dynamic and static conditions for 60 and 50 degrees also. I didn't put it here. The thermal properties, we used a special piece of equipment, the K2 Pro, with a double needle sensor. It works more or less like one needle heats up the sample, the other captures the signal, and it can measure like this, the thermal conductivity and the specific heat. So we put the samples in an oven and we took them over time, 1 hour, 2 hours, 3 hours or so. We stacked the samples on the double needle sensor and we wrapped this all in plastic and we submerged that in water with a very stabilized condition. And when the temperature was very stable, we had these measurements done. And finally, as an additional data, we tried to calculate the convective coefficient. We have 2 pieces of aluminum specially done for that, and they were more or less the same size of a Yacón slice before and after drying. So we made them with specific diameters. We had a hole done on the side, and this hole was exactly the size to fit a exposed junction thermocouple. So we had all this on a tray, on this removable trays from the oven. We put all of this in the oven and we had a temperature profile acquired over time. And we used the lumped capacitance method that considers that conduction is much faster than convection. And we had a temperature curve, the experimental and the calculated, and we tried to optimize the convective coefficient to have the 2 curves as close as possible. So we begin the result section with this photo that I like very much. It shows the importance of blanching the sample. So these are pieces from the same root, but the one in the middle was not blanched. So Which piece would you like to buy in the end? We begin with a discussion about the soluble solids content. We see here for the 4 samples, for the 4 roots from the same box, there was a significant difference in soluble solids content. That's to say, sugars. So sugars can change the relationship between water and the solids, and we had this fear that a different soluble solids content would change the behavior. But when we have the vapor sorption isotherms taken, we can superimpose them and see almost no difference. So the difference exists, but it is negligible in this case. The vapor sorption isotherms are type 3, and we cannot see any visible hysteresis, and the Guggenheim, Anderson, and the Boer model did represent them very well. So as for the drying rate, we can see here that there was no constant rate periods visible. That indicates that the diffusion is the limiting factor here, the diffusion from the solid matrix, and the harshest condition with the higher temperature, with the lower relative humidity, was the one with the most stable, the most reproducible results. That may be due to the stabilization process of our chamber, because when the humidity lowers, there's a spray of water trying to stabilize it, and every time water is sprayed, the temperature drops. So maybe this effort may cause the results to be not so stable. So these are some photos we took with that microscope, just one set of photos. You can see here that the shrinkage is very significant, so we cannot leave that out of our model. It's impossible. And in the height direction, the shrinkage was even bigger. And we can see here that the error bar is very large in some of these tests. This is due to the measurement method, because it was done with a micrometer, and in some cases, these dents, these irregularities appeared. When a sample is fresh, it seems smooth. There's no difference between one point and another. But when we measure on the same point over time, some develop these dents and some do not. So the error bars are big, that's normal. And for the thermal properties, we can see here that when the sample is almost fresh, we have no difference between these properties and those of water. Well, it's very close. And as the drying goes on, the curve gets closer and closer to the properties we have in the literature for carbohydrates and fiber. And this is one of the curves we have obtained with the test with the aluminum samples. You can see here that there is this ascending portion and this stable portion. We used this ascending portion for our calculations because the convective coefficient is a heat transfer parameter, and we need some actual heat transfer happening, and it is happening here, maybe not here. So we can see here that the bio number is very low, much lower than 1. So that is an indication that our method is valid. And the convective coefficient for the biggest cylinder was bigger than for the smaller cylinder. And anyway, the convective coefficient is always between 17 and 24. And we will use this data for our modeling later. So we begin the conclusion with this photo of the final product. This is also another reason that we cannot measure the height with the focus of the microscope. We consider that, but we can see that the sample detaches from the tray. So that's impossible to do. We need to use the micrometer. And we can conclude from this that different samples did not cause different behaviors, especially in the vapor sorption isotherms. And our drying oven seems to work better with a harsh condition, so we use them for the next tests for reproducibility. And we have a limiting factor, that is water diffusion in our samples. We need to consider that in our model. And finally, we have all the kinetics, the thermal properties, the shrinkage, all this data that we need for the simulation step that comes later. Right now, in this year, we will begin the microcharacterization step. That is to take a closer look into the sample to know if the structure is maintained, if it forms spores, if it collapses during drying. Also, we will try to measure the fiber content, the fructooligosaccharides, the inulin, to see if they were preserved or destroyed. The modeling part is already started. We have an initial model that is being presented here in FoodSim by a partner. And finally, we always try to see if this modeling is correspondent to the reality. So these are the references used in this work. Mandatory thanks to our financing agencies, FAPESP and CAPES, that have paid for this work. And thank you everyone for your attention. I'll be glad to answer your questions if you have any. And this is my contact info if somebody is interested. Thank you.